Well, good morning, everybody, and welcome to the FIA's
Morning.
Friday morning System Syzer presentation that we're about to conduct. As in, as tradition holds, if you will, what we typically do on these Zoom presentations is I'm going to make sure that everyone's muted, and then there'll be a chat button, a chat feature at the bottom, where you can type in a question. And or at the very end of the presentation, we will, we'll open it up. So if you do have some leftover questions that weren't answered properly or didn't have a chance to get answered, we'll try to address them then before we sign off. And so without further ado, I guess I'm just going to jump right in and talk to you a little bit about this very cool hydronic calculator called the B&G System Syzer. I actually found a picture of this that was out at Bell and Gossett. They originally had a System Syzer from 1939, and it was the beginning of what this became, but it was a little different. It had to do with picking a circulator based on the amount of radiation you had upstairs, which is also obviously based on the total heat loss of the building, which would affect the size of your boiler and your pump, etc. So they had this like little slide rule calculator called the System Syzer. But it had morphed. And here's a kind of a picture of the sheath, if you will, that houses the round plastic wheel. This kind of a pretty useful tool. If you're familiar with the air side of the business, there's a thing called a ductilator, which is very useful in terms of sizing ductwork and transitioning and dealing with air pressure, air side pressure drop, etc. In the engineering community, it's not uncommon for them to refer to this System Syzer as a pipelator, their version of the ductilator for pipe sizing and pressure drop and flow rates and all of that. So the intention this morning is just to kind of either review if you've already seen it and have it and just want to kind of touch up on it, or introduce it as possibly a new device for you and see the benefits of it, why it is so pretty useful in the hydronics industry. In fact, at the end of this, we'll be doing an email to everyone that attended, and in that email blast will be kind of a link to Dropbox, and in there you'll have the technical manual on how to use the System Syzer. There's going to be a couple of articles in there as well, and a certificate of attendance. So if someone needs that, it'll be available in that Dropbox, which will be a link in the follow-up email. So this is what the original, in terms of this calculator, System Syzer looked like. And it was made by, which everyone in the company is giving me a hard time that I think he must be my best friend, but Gil Carlson. So Gil worked at Bell and Gossett for about 42 years, and he was known in the industry as the father of modern hydronics. And if you've been to any of our classes, either in person or even just over the last couple of months on Zoom, you'll hear his name fairly frequently when we're discussing things hydronics. He was quite the genius, I guess you could say, within the hydronics industry. So he built this at home, and it was just a convenient tool for himself because he was constantly designing, troubleshooting, laying out, helping, speaking. And so instead of always reaching for various books and charts that all this information existed, he just wanted to make it easy for himself. So he created a wheel. And one day at Bell and Gossett, one of the sales or marketing management people were walking down the hallway and kind of stuck their head in Gil's office. And there he is sitting there with a cigarette in his mouth, and he's playing with this big cardboard wheel. So the guy went over and said, "Gil, what is this?" And he explained. And the marketing guy says, being a marketing guy, "Hey, we could probably do something with this." And so they did. And right before Gil retired, there was a gentleman, Jim Hope, who was kind of a bigwig at Bell and Gossett at the time, and they were good friends. And so Gil said, "I'm going to give this to you before I retire," and he did. To my friend Jim, Gil Carlson, and it sits on a stand here, a tripod, at the Bell and Gossett Little Red Schoolhouse, kind of in the foyer in the entranceway, as a kind of a tribute to all the things Gil did for the educating the hydronics community. But here's how it exists today as a plastic wheel, and it's been around a long time. Hundreds of thousands have been handed out over the years to the wholesale community, to the contracting community, to the engineering community. It's just a very useful wheel, if you will, or calculator. So there's 5 scales. There's not really a front and a back, other than you can say, okay, start with 1 and work your way around it. So scale 1, 2, and 3 reside on the front side of this calculator, and then on the back side, if you will, scale 4 and scale 5. So my intention this morning is just to talk a little bit about each one of these scales, what it does, how you can use it, how it's very quick and convenient, you know, in terms of some of your day-to-day hydronic, you know, system design, troubleshooting out in the field, wherever you fall within this hydronics industry. It's a pretty good tool. Dan Holohan, kind of a famous industry writer, wrote an article, The American Express Card of Hydronic Heating, Don't Leave Home Without It. You know, it was a pretty poignant article just describing how useful it is. And to be quite honest with you, all of the FIA sales guys, they all have these, you know, in their car somewhere or their job folder. All of our inside salespeople all have them at their desk or in a drawer on their desk, because it's just such a useful tool. Of course, there's an app for that, right? We're in the day and age of apps. We talk about it with our Wi-Fi thermostats and what have you. Well, B&G offers an app on the Apple Store, iTunes Apple Store. You just type in Bell & Gossett, and System Syzer will pop up, and you can download it to your phone or to your iPad. One of the benefits of this online or app, if you will, calculator, greater range of pipe sizes, added PVC, includes English and metric units, handles fluids other than water, and they incorporate the circuit setter wheel, which is another whole wheel having to do with using circuit setters to balance a hydronics cooling or heating system. I personally, most times I'm just referencing the wheel, the plastic wheel, just out of habit. But I do have it on my iPad, and sometimes it is pretty useful when you can get into different fluids and percentages of glycol. The wheel itself is based on 60-degree water, plain water, no glycol, and the pipe that it's being used, and we'll talk about it in more detail, but it's just Type L copper and iron pipe, black steel pipe on the plastic wheel. So kind of jumping into it, scale 1. Scale 1 references, or the relationship, I guess is a better way to put it, the relationship between heat transfer and flow. And when we're talking about that, when we say flow, we're going to be referencing this right here. It's a flow rate in gallons per minute. So we'll talk a little bit about that. And just to kind of provide some definitions here, NBH, in this white band here is where our BTUs will reside. And so what we're saying here is there's a relationship between BTUs, flow rate, and the third part of that equation is delta T, the temperature difference. And the other thing, one other thing to point out is the reason we're saying MBH, or thousands of BTUs per hour, is just so we could fit the different size capacities. So if I look at the number 100 right here as an example, that's really referring to 100,000 BTUs. And all I'm going to do is I'm going to line up whatever my load is, whatever my BTUs are, opposite my delta T, my design delta T. And then just simply line those two numbers up and read in the small white window here where it says GPM, and that'll be the required flow rate to move that load at the desired delta T. It's as simple as that. Now, behind that scale, what's going on here is a formula, a heat transfer formula. And that formula can be reversed. You can kind of push it back and forth or what have you. But just very quickly, what we're saying here is the heat load. Well, the heat load in BTUs per hour, or BTUH. Now you take that BTUs and you divide it by this, 500 times delta T, the temperature difference, or the design delta T. The 500, where is that coming from? It's a constant for standard water properties. What we're referring to is there are 60 minutes in an hour, 60 minutes in an hour, right? And the weight of a gallon of 60-degree water is about 8.33 pounds. So when we're finding flow rate in gallons per minute, and we're talking BTUs per hour, we want to take the 60 minutes, times it by the weight, times it by the delta T. That number is then divided into the load, and that will allow us to establish what is the desired flow or required flow rate to move that many BTUs out to where the people are, and in doing so at that certain flow rate, experience the design delta T that we calculated when coming up with this flow rate. So that wheel is that formula, basically. So before we go any further, just a quick definition, what is a BTU? We use it all the time, almost every day, that word's coming out of our mouth, of that expression, BTUs per hour. So what is it? Well, the simple definition, 1 BTU, the amount of heat required to raise the temperature of a pound of water, which happened to be about a pint, 1 degree Fahrenheit. This gentleman right here, if you've seen some of our classes, you might have seen that picture before, but Thomas Treadgold wrote the first book on heating. It was titled The Principles of Warming and Ventilating Public Buildings, published in 1824. He was kind of an engineer / inventor, and spent a lot of time learning and establishing design criteria for heating and ventilating. He actually was the one that designed the heating and ventilating for the House of Commons in London back in the mid 1800s. So he came up with the expression. He's from England, so he called it a British thermal unit. And a British thermal unit was to take a pint, which was a pound, of 62 degree water and increase its temperature to 63. And he said, I wanted to come up with an expression to describe that additional energy, or that change in temperature. And so he decided he was going to call this 1 pound, 1 degree Fahrenheit, a British thermal unit. So when we say 100,000 BTUs, we're talking 100,000 British thermal units, or whatever the number is. But it's an expression that a guy made up that we live and die by. So a while back, I got a call from a contractor who was dealing with a homeowner that had a jacuzzi, and he wanted to size a plate and frame or a brazed plate heat exchanger coming off of his existing boiler plant, so that he could allow the consumer, the customer, could raise their water temperature 30 degrees. They would maintain it at 75, and then when they wanted to use it, they'd take the cover off and they'd hit a button, and they wanted to bump it up to 105 degrees Fahrenheit. So he was asking me, how do I size the heat exchanger? How many BTUs do I need? And there's a time element that comes into play here. Because if you just take the simple 600 gallons, times it by the weight per gallon, so 8.33 pounds per gallon, times the temperature, or delta T, 30 degrees, the answer is 150,000 BTUs, 149,940. In an hour's time, you could take 600 gallons and change its temperature 30 degrees. Now, generally speaking, especially like a jacuzzi or a hot tub, that's going to be unacceptable to most clients. They're going to want it a little faster than that. So you say, okay, how do I calculate it if the customer does want it? Maybe they want it in a half an hour. How many BTUs is that? Well, basically, you're just taking what the load is in an hour and times it by 2, because you're only giving it a half hour to get there. So 300,000 BTUs to take 600 gallons and raise it 30 degrees in 30 minutes. If you, one more extreme, say, hey, I want it in 10 minutes, which is probably unrealistic, but just for argument's sake, do the math. 149 times 6 increments of 10, increments of 10. I'd need 900,000 BTUs to take 600 gallons, change its temperature 30 degrees in 10 minutes. But that's that whole relationship of BTUs, delta T, and then a time element. So getting back to scale 1, states the relationship between load and flow rate, gallons per minute, delta T, temperature drop or rise. If we're in chilled water, that water temperature is going to rise. It's not going to drop. It's going to actually increase as it's removing the heat across the coils in the space where we're trying to air condition or condition the space. MBH, we talked about it, thousands, GPM, circulation rate in gallons per minute, required to convey the design BTU load at that design temperature difference. So just let's work through a couple of quick examples. And one of the things I think I hopefully will remember to mention this at the end, but at the end, I will ask everyone to just email me. Anyone who does not have this wheel and would like one, just email me with an address and where you want it mailed, and I'll have the office mail them out to you, as well as that email that I'm going to send you with the Dropbox, where you can actually download the PowerPoint presentation as a PDF format, as well as the actual TEH manual that Bell & Gossett made with instructions on how to use the wheel. So I take the wheel and I say, look at the load. The question is this: how many gallons a minute do I need if I have 100,000 BTU load and I'm designing on a 20-degree delta T, which is a very common number, 20-degree delta T, in the hydronics industry. Not limited to, but pretty common. And all I'm doing, take this wheel, scale 1, and I'm going to manipulate the wheel itself until I have 100, which represents 100,000 BTUs lined up opposite that 20-degree delta T. Then just read straight down in the small window here where the highlight is GPM, and you'll see that it's 10 gallons a minute. So 100,000 BTUs, 20-degree delta T, I need 10 GPM. That's half of the equation of sizing a circulator. What's the flow rate, and then what's the pressure drop? So what if I had the same example and I was designing around a bigger delta T, say 40 degrees instead of 20? Same exact exercise, line up the 100 opposite now the new delta T, which in this case is 40. Read in the small window, 5 GPM. So right off the bat, you're seeing there's this inverse relationship when you have a given load and you start to increase or decrease the delta T. You'll increase or decrease the flow rate, which means it could change the size of the circulator, change the size of the piping, size of the pressure drop, the energy required to move it. So there's different design criteria that you can start to implement, and this wheel is very helpful in letting you kind of analyze back and forth. So say I had a snow melt system, and the load was calculated that it was going to be 600,000 BTUs to melt this driveway, maybe this large residential home. Not uncommon in the radiant world, in the radiant tubing manufacturers world, when they're designing a snow melt system, to use a 30-degree delta T instead of the more traditional 20. You get a little more leeway because no one's laying on the ground like in a radiant system in a family room. This is just trying to melt the snow. So it's pretty common that they'll pick that 30-degree delta T. It just allows for sometimes a little smaller circulator, which means the upfront costs can be reduced a little bit. So again, same exercise, take the 600,000 BTUs. I want to line it up opposite my design delta T of 30. I'm going to read in the small window, 40 gallons a minute. 40 GPM will move 600,000 BTUs when you design it on a, say, maybe 120 to 90 or something like that, or 130 to 100, and you're doing that 30-degree delta T. Another question, again, just a couple quick examples to be using the wheel, or once you get it, to be able to use it again. Determine the flow required for 150,000 BTUs at a 30-degree delta T. So all again, it's just an exercise getting used to this scale 1. Find the load, 150,000. So here's my 100, here's my 200. So right in the middle there is my 150 opposite the 30. I'll see I need 10 gallons a minute to move 150,000 BTUs, which I just told you earlier, I needed 10 gallons to move 100,000. So how can I do 150 with 10? Well, the answer is this. I'm allowing a little greater, a bigger delta T, a 30-degree temperature drop. So just quickly moving over to a chilled water application. Determine the flow rate or required flow for 20 tons of cooling using a 10-degree temperature change, or delta T. So a ton of cooling is representative of 12,000 BTUs an hour. So 20 tons times 12,000 would be 240,000 BTUs. Or in our example here with the wheel, it would be 240 MBH. What I want to point out, which I didn't at the very beginning, is notice right here, GPM/per ton, GPM per ton. 2 gallons a minute per ton, 2.5 gallons a minute per ton, and 3 gallons a minute. They basically line up opposite, pretty close to an 8-degree, a 10-degree, and a 12-degree delta T, or temperature rise. Somewhere in those three, and 10 being the most common, is typically the range in a chilled water application where they're allowing for this type of temperature rise. So you're leaving the chiller plant at 42 degrees and you're coming back at 52 or something to that effect. That would be a design delta T of 10. So in this case here, the 20 tons, which is represented by 240, so 210, 220, 230, 240 right here, opposite 10, I could read in the white band here, the GPM pointer, saying it's about 48 gallons a minute to move 20 tons of chilled water. So just a real quick side note, 1 ton of refrigeration. So 12,000 BTUs per hour. So what they did is heat was added to melt 2,000 pounds, which is a ton, 2,000 pounds of 32-degree ice, and they wanted to change its state. They didn't want to change its temperature, but they just wanted to change its state from 32 degrees ice to 32-degree water in 24 hours. This equaled 288,000 BTUs per day, or 12,000 BTUs per hour, which is where we come up with this 12,000 BTUs per ton. So you're out in the field, you're in a mechanical room, and you want to know what's the actual load on the building at that given time. So you see the water leaving the boiler at 180 and coming back at 160. And by using the pressure drop across the triple duty valve with a gauge, you establish that this pump is pumping 600 gallons a minute. What is the actual load on the building? What's the actual total load? Well, the way you could approach that is right now, am I looking for flow rate? No, I've already established it. So I'd still use scale 1, and I'd line up 600 GPM opposite what? Well, it left at 180 and came back at 160. So find the GPM right here, 600. So now I'm using this wheel kind of working backwards. And I find the 20-degree delta T, and I realize that it's 6,000 MBH or 6 million BTUs at that given set of conditions. 600 gallons a minute, 20-degree drop, the load of 6 million BTUs. So it's just another way to quickly use this wheel. Moving on, scale 2. Scale 2 and 1 and 2 don't work together. And what I mean by that, don't work together, they don't have to line up with each other. You use scale 1 to find your flow rate, and then you go down to scale 2. Now you're saying, okay, I know my flow. What size pipe? What's a good industry standard practice to select the proper size pipe to establish the friction loss that I'm going to need to calculate so that I can select a pump that can provide the necessary pressure differential, the head loss, while moving the appropriate flow rate, gallons per minute. So on the wheel, scale 2 references flow rate for the friction loss for both type L copper and schedule 40 steel pipe. There are 2 different measurements of friction loss. One of them is milli-inches per foot, which we're never going to talk about again, but just recognize that it was there. It was useful very long time ago when systems were being converted from perhaps gravity hot water to a pumped circulator. The piping was so large because it was able to provide flow with gravity, and all of a sudden you have this electric motor and an impeller or centrifugal pump. The pressure drop was very low, so they started using milli-inches. But today, everything we're going to talk about, and basically everything you would typically deal with on a day-to-day basis, is going to be in feet. Feet, and the way the scale is listed is it's feet of head loss per 100 feet. So we'll talk about it. We'll get into it. So scale 2, right down here, and the type L copper is the top window here, and then the iron pipe is the second option. This is where I'm looking for flow rate. You see it says GPM is identified. And generally speaking, as a quick rule of thumb, as you're rolling through, as you're manipulating the wheel, you want to have that flow rate typically fall somewhere within this white triangle here. And you'll see that the friction loss is right around 4.5 feet per 100 feet would be the max. And you'd be down as low as a little bit less than 1. But typically you're trying to find the flow rate when you're first initially manipulating scale 2 in this band, and then obviously it has to line up very specifically opposite a particular pipe so you can establish the pressure drop. So determine the pipe size for 10 gallons a minute in a hydronic system. So let's say I'm going to use type L copper and I'm looking for 10 GPM. So what's happening is as I manipulate this wheel, the first size pipe that I come across where this 10 kind of falls somewhere in this triangle is 1.25 inch copper. And then what I do is I find the 10 GPM and I just read straight up. And it looks like it's almost listing, it's about 2.5, 2.6 feet of head loss for every 100 feet of pipe. So if I have a circulator and that circulator is trying to move 10 GPM in this 1.25 inch pipe, for every 100 feet of pipe, that circulator has to be able to develop at least 2.6 feet of pressure differential or head to overcome that resistance of moving 10 GPM inside that 1.25 inch pipe. That's the extent of this scale. Same question, just 5 gallons a minute. So now I'm a little lower flow rate. You'll see right away that I can also use smaller diameter pipe. So there could be some economic benefit there. And again, as I'm rolling through, I'm dealing with copper pipe for the example, 5 GPM. I'm lined up right across the arrow to 1 inch. I have a head loss, a frictional resistance loss of about just under 2 feet, 1.9 feet for every 100 feet of pipe. And that's how I would read this scale, how I'd use it. So now, determine pipe size for 70 gallons a minute in a typical hydronic system. And this is a quick example of where you might have a couple of different answers. So as I manipulate the wheel, the first pipe size that I come across is 2.5 inch. And the 70 is falling within this band here. And I see it over here. So it's right about there, about 3.5 feet for every 100 feet of pipe. And it would technically, it's a good selection and not a problem. If I continue moving that band and I continue to manipulate in that 70, you'll see that it also still stays within this triangle here. And I come across the next size pipe, which would be 3 inch. And obviously with the 3 inch, because it's a larger diameter, moving the same flow rate, I am going to have, lower pressure drop, lower frictional resistance, 1.2 for every 100 feet instead of 3.5. Which way do I go? Well, generally speaking, a lot of times it's economics, and a lot of times they're going to say, hey, upfront costs, I can buy that pipe, the 2.5 inch pipe and fittings for less money than the 3 inch pipe and fittings. That might be a reason, that might be a direction. If you look at operating costs over the life cycle of that system, more money up front, the 3 inch, absolutely, but less pressure drop, less energy required to move my desired flow rate. Maybe I'm looking at it from that perspective. And if that's the case, I might be picking 3 inch and saying, yeah, it's going to cost me more money up front. But if I look at the life of the operating cost of throughout the life of this project or this, cooling or heating application, maybe I'm better served, or the client, the customer is better served with the larger pipe and the lower energy requirement. So this is the one example. Scale 3 actually works with scale 2. And scale 2 is the pressure drop, friction loss in feet per 100 feet. Scale 3 establishes how fast is the water moving. What's the velocity in feet per second? And we have kind of two criteria. We want it to be fast enough, high enough to carry any kind of entrained air that might be in the water stream. So typically on the low side, when I pick a pipe, I want to make sure it's not any slower than 1.5 to 2 feet per second. And then on the high side, I have kind of two different criteria. One of them is going to be a noise consideration, and the other one's going to be a erosion corrosion consideration. So whenever I'm talking about comfort, when I'm talking about residential, commercial, apartments, condominiums, hospitals, where you don't want to hear that type of noise, you typically don't want to pick a pipe with a pressure drop, a velocity, a feet per second, any greater than about 5. If you're in some type of manufacturing commercial application where there are other noises, so noise is not going to be your design criteria, then you can get as high as, really typically no more than 8 feet per second with this copper pipe or this black iron pipe. So that's the range, 1.5, 2 on the low, 4 to 5 on the high, and also it's a commercial application, then I might be going as much as 8. This is just a quick picture. What it's showing here is if I have air bubbles, entrained air bubbles in the stream of water, and this might be like a return riser coming back down, heading to the mechanical room. As long as the velocity is greater than 1.5 to 2 feet, any of these entrained air bubbles, even though they're somewhat buoyant, they'll be dragged back with the velocity of the flow back to the air separator in the mechanical room. If I'm less than that, I'm lower than that, they're showing here even as slow as a 0.5 foot per second. These bubbles, the buoyancy of these bubbles are greater, and they will float back to the high point and get lodged up in some air handler or some top floor baseboard or what have you, and can have some negative impact in regards to heat transfer and even flow. So this is one of the reasons with this entrained air, this is why we want to keep that slow side as no lower than 1.5 to 2 feet per second. So works with scale 2. So once I've established a pipe size, say on scale 2, and I've lined it up and I've found my pressure drop and all of that, without moving anything, I just glance down and I find the flow rate that I was concentrating on, and I see where it intersects the scale here, the velocity feet per second. And if it's a heating application, heating or cooling where noise is a concern, I want to make sure that that flow rate doesn't get any greater than this 5 feet per second. If it's a commercial, industrial, noise is not a concern, then I might have a little more leeway and I could be as high as, but I don't want to go past this, 8 feet per second. So find the velocity for 10 gallons a minute flowing an 1.25 inch pipe. So I take that scale 2, I have it lined up opposite the 1.25 inch copper. I found my 10, I know my pressure drop. Now all I do is I quickly look down here and I say, okay, where does it intersect? And you'll see that it's right there, right about 2.3, 2.4 feet per second. It's fast enough and it's not too fast. It's a good selection. Continue with the same flow rates, 5 gallons a minute. I decided I was going to use 1-inch copper pipe for the 5 GPM application. Find my pressure drop without moving the wheel. I just glance down, find the 5. Where does it intersect? And you see it's right there, right about 1.8 feet per second. So it's still fast enough. It's above the 1.5, and it's not too fast over here on the 5. So what is the velocity of 1,600 gallons a minute flowing through an 8-inch pipe? So I line up the 8-inch in scale 2, so I know that I'm lined up, iron pipe. I'm going to find 1,600 gallons a minute over here, and you see that I have 2,000 and 1,500. So just a little bit north of that 1,500 gallons a minute line, I'm going to say that's my 1,600 GPM, and you'll see that I am exceeding the design criteria. I'm moving too fast. The velocity is too high. I could actually have corrosion take place internally with the water actually beating the pipes, the walls of the pipes, that the fittings and turns and stuff would be just so turbulent. So really, that's a bad selection. I'd have to go to the next size pipe. And in this case here, the next size pipe up is 10-inch. So same thing, line it up in scale 2, find my 1,600 gallons a minute. Where does it intersect? Well, it's well below the 8, so I'm in good shape. That would be the better selection. Scale 4. So scale 2, scale 3 is pressure drop and velocity. Scale 2 and scale 3 are the one time where the scales work together. So once you have established scale 2 and you know your flow rate, you know the pipe size, you know the pressure drop, just glance down to 3, make sure the velocity is not too high. Scale 4 is of all of the tables, probably the least useful of the 5 scales. And the reason for that is, every phone, every watch, for God's sakes, every iWatch, we have calculators everywhere. But when this scale, when Gil made this and when they converted it from the cardboard to this plastic, virtually no calculators even existed back in the 60s. And so it became like it was used to calculate total pressure drop based on your total length of run. So determines the required pump head based on the resistance per unit length, and as well as what we refer to as TEL. So what we have to account for is not only a straight run of piping, but what are the fittings? because fittings offer greater resistance to flow than a straight piece of pipe. So we got to calculate that to establish the TEL, the total equivalent length. And there are tables in the sheath that actually comes with the System Syzer on the backside. You know, it actually lists some of the old steel and cast iron, you know, regular fittings, long radius, etc., and what their equivalents are. So for a quick example here, if I had a 90-degree regular cast iron 4-inch elbow, it's saying that TEL, that 4-inch elbow represents 11 feet of straight pipe. So I'd want to add that to my actual straight so that I can accommodate all of the frictional resistance that flow rate's going to experience in that piping network. And so that's what scale 4 is all about. A rule of thumb that's been used for a long time and usually pretty effective is instead of trying to find all of the T's and the elbows and all of the valves that are in that network, they'll say, okay, whatever your straight run is, add 50%, multiply it by 50%, and that will become your new TEL. And then you can use that to establish the total pressure drop within the system. Because on scale 1, you found the pressure drop for every 100 feet of pipe. Well, if you have 500 feet, we'll plug that in here, add your 50% for your fittings. All of a sudden, at 750 feet, you know, it would line this up, and then you could, this small little wheel right here, or window, I should say, will say, hey, this is your total pressure drop for that application, that circuit. So again, staying with some of our original calculations or flow rates, if I have 10 gallons a minute and I establish what my pressure drop was going to be in 1.25 inch copper pipe. So 1.25 inch, I establish the pressure drop. I add 50% to this 200 feet to get my TEL. So that becomes 300 feet. So now I'm taking my 300 feet over here in the white band. I'm lining it up opposite the pressure drop, which we established was 2.6 on scale 2. And then I look down here and I say, okay, my total pressure drop is going to be about 8 feet, just under 7.5, 7.7 feet ahead. So call it 8 feet ahead. So that's how I use scale 4. Is it becomes a calculator of the total length of the run. Just real quickly, say I had 60 feet of 1-inch pipe. And I established, 60 feet times 50% is 1.5 is 90 feet. I established what my pressure drop was. Here I am, 1.9, which is what I found on scale 2. I line it up opposite my 90 feet, which is my TEL. And I read down here and I read this total pressure drop. It's like 1.7. These are easy numbers to work with, but years ago when you didn't have a calculator, it was pretty useful. It's not as useful or as needed today. So then you can ask the question, what is the total pressure drop in a pipe with a TEL of 130 and a flow rate of 200 gallons a minute? Well, the first thing you'd have to say is, what pipe do I need? What's a good industry selection to select 200 GPM? And in using scale 2, using the wheel and rolling it around, I come up with 4-inch iron. There's my 200 gallons a minute. And it's a pressure drop of about 2.2 feet for every 100 feet of pipe. And then the question up above is, if I have a TEL of 130, what's the total pressure drop? So then I would take that and I'd go to scale 4. I'd find 2.3 over here, and I'd line it up opposite my TEL, which we said was 130. So 2.6 opposite 130. My total pressure drop, the calculator calculates 3 feet of head loss. So this is kind of a weird way of approaching it, but it is sometimes used as an application. The pump you selected will provide 50 feet of head at the design flow rate. The TEL of the longest circuit is 1,500 feet. What friction loss rate should the pipe have? So we're kind of working backwards, but what we're saying here is we're handicapped at 50 feet. We can't provide any more head loss than 50 feet. We know the circuit's 1,500 TEL. So as I'm picking my pipe, what frictional loss should I be using when I select my pipe? So there, what we're saying is I have 50 feet of head loss here, and I have a TEL of 1,500 feet. So there's 1,000, there's 2,000, there's 1,500. So I should be picking the pipes on scale 2 at a frictional resistance of about 3, no more than 3.4, 3.5 feet of head when I go on scale 2 to pick my pipe. And in doing so, if I do that, I know that I will have the desired flow rate, and the pump will be able to provide that 50 feet ahead, and he'll be able to overcome the frictional resistance of 1,500 feet of piping and fittings. So pick 3.4. So last scale, getting close to winding this down. Scale 5 is by far, it could be the most useful, and at the same time, especially at the beginning, the most confusing scale of the 5 scales that are on the System Syzer. Scale 1, 2, and 3, very useful. You can use them all the time out in the field, pipe sizing, pressure drop, checking, making sure, figuring out to select the pump. Scale 5 can be very useful, but like I said, it can be a little bit confusing. So it's based on the relationship that exists between flow and system resistance. And what I mean by that is the head will vary approximately as the square of the change in flow. It's kind of a wordy sentence. This is what scale 5 is built around. You have a known flow and a known head. I'm going to pick a new flow rate within that same system, that same piping network. I can calculate mathematically what the final head, the new head loss, is going to be. So let me spend just a second here on this. If we were looking at this wheel, and we had done a calculation, and we had figured out that at 50 gallons a minute, I was going to have 3 feet of head loss for this given circuit, whatever it is, feeding something, maybe a fire tube boiler that has very, very low pressure drop. So 50 gallons a minute, 3 feet of head loss. Within that same circuit, that same system, if I said, hey, what happens if I doubled the flow rate? Would I double the head? And the answer is no, it's a squared relationship. So if I took 50 GPM and I had a head loss of 3 feet, and I look at 100 gallons a minute, I don't manipulate the wheel. I've already got my known conditions lined up. I find the new flow rate, and I look at the new head loss, and it would be about 12. And that's because the relationship is squared. And so if I went from 50 to 100, so 100 divided by 50 is 2. 2 over here squared is 4. 4 times my original head loss of 3 becomes 12. That's the Fanning's formula. That's the relationship that scale 5 is built on. So a chiller manufacturer says, look, when you're moving 100 GPM through my barrel, I have a head loss of 12 feet. That's a published number somewhere on their literature. The question is coming maybe from an engineer or a facilities person saying, hey, what's the head loss at 150 gallons a minute if I want to increase the capacity? So the way I could use scale 5 is I would say, okay, 100 lined up opposite 12. Without moving the wheel, just find the new flow rate, 150. Look at the new pressure drop. It's going to be about 27 feet. So I go from 12 feet to 27 feet when I pump 50 more gallons a minute in that barrel, that chiller barrel. So that's a way of using scale 5 real quickly. Just, I have a known flow and head. If I change that flow, what's the new head going to be? What's the head loss? Another example that we use, and today almost everything's going to be software, so the software is going to calculate these system curves. I'm just going to show you old school how we would have done it in the past, but it's also important to know what the software is doing, know that it's, how it's being generated. So a closed system has a flow rate of 200 gallons a minute and a head loss of 30 feet. Plot the curve. So what would happen is the known set of conditions of this, 200 GPM at a pressure drop of 30 feet ahead. What I would do is I would just arbitrarily pick some other conditions. And again, without moving the wheel, keeping the wheel right there, I say, okay, at 100 gallons a minute, 7.5 feet. 150, 17. 200, that's my known. 250, it's going to be almost 46 feet, and 300, and I'm arbitrarily just picking these numbers, it's about 67. And I would take those numbers and I'd plot them on a pump curve, and I'd create this system curve, and I'd see where does my pump curve intersect, and that's going to be the operating point for that given system. If 200 at 330 feet is accurate, if that's the known, I build these arbitrary points so I can build a curve, and where it intersects the actual pump curve is where the pump is going to be operating in this system. So just let me apply real quickly one other example. And this is something that we have done as far as providing a pump for someone that has an application where maybe the set of conditions that they're trying to achieve aren't landing exactly on that curve. What happens? So the conditions are this: 20 gallons a minute at 15 feet ahead. Maybe it's 200,000 BTU, pressure drop, Giannoni water tube heat exchanger boiler, and it has a fairly high pressure drop for the 20 GPM. I want to know what's going to happen here. So these are my options for the pump to meet this set of conditions: 20 at 15 feet ahead. So what do? I line up my system Syzer scale 5 at 20 opposite 15 feet ahead. And then once I have that, once I have 20 opposite 15 feet, I will just arbitrarily pick these other flow rates and their corresponding pressure drops, and I will plot a system curve. So I'll connect these 4 dots and I'll just make a curve. And I'll say, okay, based on this set of conditions, 20 at 15, this pump, which is a little smaller, is going to operate right there. This pump, which is a little bigger, is going to operate right here. What kind of impact does that have on either one of these selections, or either one of these pumps relative to the operation of whatever device, a heating system or whatever it is? If I provide a little less flow and I'm still trying to move 200,000 BTUs, say, what's going to happen? And if I provide more flow rate than I need, the 20, what's going to happen? Well, we already talked about this on scale 1. To move a certain BTUs with a different flow rate, you're going to change your delta T. You're either going to increase it or decrease it. And the point of using system Syzer and scale 5 and the system curve is if it's only 1 or 2, maybe 3 degrees, it might not even be a difference, might not be enough of a difference. You could select that smaller pump or that bigger pump. But this is where system curves intersect pump curves. Now you know exactly where the pump's operating in that system. But it all starts with this right here. This has to be factual: the flow rate and the desired design head loss. Once I know that, I can build a system curve and I can figure out exactly where that pump is going to operate, any one of those pumps on that system curve. The last thing I just want to share with you on scale 5 is it can be used to select control valves in accordance with their C sub V rating. It's a flow pressure drop coefficient. So a CV rating, what it means is the flow across the valve in gallons per minute that creates a 1 pound pressure drop or pressure differential. Whatever flow rate that is across that valve's orifice to cause this 1 pound drop becomes that valve now has this known CV of X, 5 gallons a minute, 2 gallons a minute, 30 gallons a minute. Whatever the flow rate was to cause that 1 pound pressure drop, which the valve manufacturer tests. Every valve has a CV rating. Ball valves, service valves, control valves, 3-way valves, 2-way valves, 4-way valves, zone valves. Every valve has a CV rating because they're all tested. And so from a visual standpoint, that's what I was just trying to say back here, is a valve, when it experiences a 1 pound pressure drop, whatever that flow rate is to cause that 1 pound pressure drop becomes that valve's C sub V rating. Now, 1 PSI I mentioned, but you could convert it to feet of head. So 1 PSI is the equivalent to 2.3 feet head loss. And you'll notice on scale 5 that it's listed both PSI on the bottom and feet of head on the top. And that's for that exact reason, for convenience. And this is a very good visual, but this is how they actually come up with the testing of these valves. So they have this tub of water, if you will. It maintains a constant level, 2.3 feet above the valve inlet, which is a 1 pound inlet pressure sitting right here. 2.31 feet is 1 PSI. The water that passes through this valve is draining into this open tub. So there's no pressure drop. There's no resistance on the outlet of the valve. So it's just straight a 1 pound pressure drop across. So the outlet at the valve, the pressure at the outlet is 0. The volume of water flowing for 1 minute, that's my gallons per minute, can be weighed to determine the GPM. And that GPM becomes the valve's C sub V number or rating. So a control valve is to be selected for 3 PSI differential at 2.9 gallons a minute. What is its C sub V? So what do I know? I know that someone said at a flow rate of 2.9, I want a pressure drop of 3 PSI. So this is my known in this particular equation or this question. So what do? I get down, the GPM right here is in the white band. He said PSI, so I'm looking down here where it says PSI, and I'm going to take my 2.9 GPM and I'm going to line it up opposite this 3 PSI, because those are my 2 known factors. And then it says, okay, pick a valve by its CV rating so that when I have this set of conditions, when I have 2.9 gallons a minute flowing through, say, a chilled water coil and an air handler, I'm going to experience 3 PSI pressure drop. And so what I do is I just go back and I read the C sub V right here. What is the CV rating? Those are my knowns. Here's my CV. It becomes 1.7 CV rating. So I buy a valve that has a CV rating of 1.7. I put it into a system that's pumping 2.9 gallons a minute, and that valve will cause a 3 PSI pressure drop. And the reason for that, which is another whole conversation, is maybe the engineer's looking for some control valve authority. And so he wants that valve to really have some impact on the output of that coil. And by really impacting the flow rate by having control valve authority, having some good pressure drop, I can control the space, pretty accurately. So that comes to the end of our System Syzer presentation. I'm going to stop sharing the screen. I'm going to open it up. I didn't know if anyone had any questions as we were going through this. Let's see here. Let me see. Open it up.
No, I'm all set.
Yeah, everyone good? If you have any interest in getting a wheel and you don't have one, like I said, just email me. What I can do right now in the chat room is I'll put out my email address real quick, and you guys just shoot me a quick email, and I'll make sure, if you just give me an address on where you want this System Syzer delivered, and I'll make sure we get it in the mail and out to you as soon as we can. So if no one has any further questions, I want to say thank you again, as we always do. Thank you for your time this morning. I hope everyone has a wonderful weekend. The weather